Hi everyone, I'm Margarida. Thank you very much for the introduction. I am a PhD student at the University of Vigo, and first of all, I would like to thank the organizers for inviting me to give this talk at QCrypt. I am very happy to be here. And today I'm going to tell you about QKD with correlated sources, a work that was developed in collaboration with Gokato from NTT Japan, Akihiro Mizutani from Mitsubishi Electric, Marcos Curti, my supervisor, and Kiyoshi Tamaki from the University of Toyama. As you know, there is a gap between the theoretic security promised by the security proofs and the actual security offered by our practical implementations of QKD. One of the biggest problems is the deviation between the idealized device models used in the security proofs and the functioning of real devices employed in our experiments. This deviation might lead to side channels which can be exploited by an attacker to compromise the security of QKD. Therefore, it is crucial to bridge the gap between the theoretic security and implementation security. Perhaps one of the biggest vulnerabilities of a QKD setup to side channel attacks are the detectors. And in fact, several attacks have shown to break the security of QKD by exploiting this deviation between the theory and the practice. Fortunately, this problem is now solved due to the proposal of a measurement device independent QKD, or its variant of twin field QKD. And in these protocols, all the detections take place at the middle node Charles, which is completely untrusted. And this means that the security proofs of these protocols do not make any assumptions on the detectors, and therefore they are not vulnerable to security loopholes on the detector side. Moreover, these protocols have a good performance, so they provide high secret key rates, and they are practical with current technology. So this means that we are pretty much done on the detector side, and the next step to prove the implementation security of QKD is to secure the source. It is typically assumed that the emitted pulses are perfect. However, as you know, the prepared signals always deviate from this perfect scenario due to inevitable device imperfections. And this can lead to side channels on the source. So for instance, we can have state preparation flaws due to the finite precision of modulation devices. So this means that we end up emitting states that deviate slightly from the desired states. It is also typically assumed in QKD that our labs do not leak any information about the internal settings of the transmitters. However, this is not always the case because one can have Trojan horse attacks. So this happens when Eve sends some bright light into the source and then observes the back reflected light to learn some partial information about Alice's settings, or also through spontaneous or passive information leakage to undesired degrees of freedom, such as frequency or polarization. The good news is that if we can model these imperfections and include them into the security proofs, then we can actually guarantee the security of our practical implementations. And in fact, these three imperfections have been quantified experimentally, and recently we have shown that they can be all incorporated together into a security proof. So finally, pulse correlations. It is typically assumed that the emitted pulses in QKD are independent. However, this assumption might not be fulfilled because there might be classical pulse correlations between the emitted pulses. Modeling and incorporating pulse correlations into the security proof is the last step to achieve implementation security. In this talk, I will show you how we can treat pulse correlations. As you will see, it turns out that this imperfection can be incorporated together with all of these. And finally, I will show you how we can prove the security of QKD with correlated sources. Okay, so let me start by first explaining in a bit more detail what pulse correlations are and how do they arise in our practical implementations. So pulse correlations are purely classical and they arise due to limitations of practical modulators, typically due to memory effects. They occur when the state of the emitted pulses depends on the previous encoding. So this means that the setting information is not only encoded into a single pulse, but also into all the subsequent pulses. So for example, ideally, we would prepare these states here, where J1, J2, and J3 are the different setting choices for each pulse. However, what we send in reality due to pulse correlations are these states here instead. And as you can see, they have a dependence on the previous setting choice. Classical pulse correlations is a very serious problem, especially in high-speed QKD systems. And in fact, a recent experiment has quantified pulse correlations in both the phase and in the intensity modulator while using a QKD setup with 5 GHz repetition rate. But despite its seriousness, pulse correlations have often been overlooked by the community for two main reasons. First, it is believed that they are very small. However, as we have just seen, at least in high-speed QKD systems, they can no longer be ignored. Moreover, the GLLP analysis has shown that even if an imperfection is small, it can in principle enhance it by exploiting channel loss. Second, it is believed that this imperfection is very hard to model because the state space becomes very large. And in fact, only a few works have considered this imperfection, and none of them deal with pulse correlations in terms of secret key information nor long-range pulse correlations. But fortunately, we have come up with a security framework to deal with arbitrary pulse correlations. And the key idea of our framework is to treat the information encoded in the subsequent pulses as a side channel to our pulse of interest. But let me tell you this in a bit more detail. So let us consider nearest neighbor pulse correlations and the three-state protocol for simplicity. However, our framework also works for arbitrarily long pulse correlations, as I will show you later, and for any number of states. So this is really just for simplicity of discussion. So in this protocol, Alice prepares these states, psi, for one of these encodings, and then she sends them over to Bob in the quantum channel. And typically in QKD, to prove the security of such a protocol, we consider an entanglement-based virtual protocol, which is equivalent to the actual protocol. In this fictitious scenario, Alice prepares her ancilla systems and these pulses in an entangled state, and then she sends the systems B to Bob. So in the case of pulse correlations, this entangled state can be expressed this way, where here A and B are the composite systems of Alice and Bob. These are Alice's ancillous states, and they form a set of 3 orthogonal states in a 3-dimensional space. And these states here are are the ones that are sent to Bob, and they represent any kind of nearest neighbor pulse correlations. So for instance, this is the state of the nth pulse when Alice selects the setting Jn, given that her previous setting choice was Jn minus 1. So then Bob receives these signals from Alice, and his detectors click for some of them. And later on, they both measure their local systems to obtain the experimental data. And note that the equivalence between this fictitious protocol and the actual protocol holds because these measurements on Alice's ancillas commute with any measurements on Bob's side. So the fact that Alice performs her ancilla measurements after these detections does not affect the statistics of the measurements or the secret key that is generated between Alice and Bob. But importantly, by using this virtual protocol, we can consider what Alice and Bob would have observed if they had measured their local systems in a complementary basis to the key generation basis. And as you learned in just the previous talk, by considering this complementary scenario, we can actually estimate the phase error rate, which quantifies the amount of information leakage to Eve. And to quantify the phase error rate, we typically first obtain the probability of a phase error by considering any attack on a particular detected pulse. Let's call it the kth pulse. And then we ensure security against coherent attacks by using concentration inequalities for correlated events, such as Azuma's or Kato's inequality, or other known techniques. So again, to obtain this probability, we are interested in the state of the kth systems just before the fictitious measurements and that resulted in a click on Bob's side. But in the case of pulse correlations, this is not so straightforward because the setting information of the kth pulse might have leaked to the subsequent pulses. But if we can estimate the phase error rate in this case, so taking into account all these possible leakages of information, then we should be able to guarantee the security of our protocol. So let me explain you this with a bit more maths. So here, to obtain the state of the kth pulse, let's first assume that Alice already measured all of her ancillas before the kth pulse. And again, this is possible because Alice's measurements commute with any operations or measurements on Bob's systems, including these detection measurements. And here we denote with a dash the outcomes of Alice's measurements. And since we are considering the three-stage protocol, this means that now these J's will be either 0Z, 1Z, or 0X. And now let us focus on all the pulses after the kth pulse, so all of these terms here. And note that you can put together this state and all of these terms, and we define a new state, which we call JK plus 1. And then this leftover part comes here directly. And then these two states can be defined as another state, lambda JK. And note that this state depends on all of Alice's ancillas and all of Bob's systems after the kth pulse. So basically, we treat all of the signals after the kth pulse as just a single state, lambda JK. And as you can see, it has this dependence on JK. So then we can write the full entangled state in this form, where again we have replaced all of these terms after the kth pulse with our newly defined state lambda JK. And importantly, this is the side channel information about our pulse K. So as I said before, we can treat all the information encoded in these subsequent pulses as a side channel to our pulse of interest. But to understand this formula a bit better, it is useful to compare it with a protocol where there are no pulse correlations. And in this case, our entangled state would be written in this way. And you can see that they are really similar. So the only difference is that here, these states that are sent to Bob do not depend on the previous setting, as they do in this case. And also, lambda does not depend on JK, as it does here. In other words, this is not a side channel information about this system BK. And as I explained before, in the security proof, we typically estimate the probability of a phase error by considering any attack on this system BK. But in the case of pulse correlations, the setting information about our kth pulse is not only encoded in this system BK, but also into all the subsequent systems. But this suggests that if we can obtain the probability of a phase error by considering an attack on this composite state, then we should be able to guarantee the security. So in summary, we can treat a protocol with pulse correlations as a protocol where Alice prepares these states, where this is the side channel state, and then sends all of these systems to Bob. Okay, so now that you understand a bit more about our framework to deal with pulse correlations, let us consider a particular device model. To understand the intuition behind this model, it is useful to consider the states that we would send in an ideal situation, so in a perfect three-state protocol. And these states can be expressed in the block sphere in this way, where we have 0z, 1z, and 0x. What we expect in the presence of pulse correlations is that these states will now depend on the previous pulse. So they will deviate from their original positions in the block sphere. So they basically can be anywhere inside these cones. And these cones could even be different for each of the setting choices. So then using this intuition, we can express our emitted state in this way, where this is the idealized state that we would send in a perfect protocol, and this part accounts for the deviation from that perfect scenario. More precisely, this is a single photon state that lives in a qubit space. This is a qubit state, and this is a state in the same qubit space that is orthogonal to this one here. And this is a relative phase that, as you can see, depends on the previous pulse. And here, epsilon quantifies the strength of the correlation. And these parameters could be expressed in the block sphere in this way. And as you can see in this particular device model, in this example, we allow the relative phase to change according to the previous pulse. So this angle theta will vary. However, we fix the amplitudes for all the states. So we fix this epsilon, or in other words, we fix this angle alpha here. Of course, more generally, alpha or epsilon would also depend on the previous pulse. So basically, we could obtain any state inside of this cone. But just for simplicity, we assume this model where we allow just the theta to vary. And of course, our framework could work for other models. So again, this is just a simple example. Also, I would like to remark that when epsilon is 0, so when we have no imperfections, our emitted state becomes our idealized state. So this means that we recover the perfect scenario where we emit perfect states. But as epsilon increases, this term reappears, and then our emitted states will deviate from this perfect scenario. And of course, the higher epsilon is, the stronger the correlations are, and the more information is leaked to a possible eavesdropper. Okay, so recall that we want to prove the security of a protocol where Alice sends these states to Bob. And these states can be expressed in this way, where this is just the definition of lambda jk. And recall that these states here, this one and this one, they represent any kind of nearest neighbor pulse correlations. So again, we just pick this particular example to model these states. So now we can directly plug it in here, and after some algebra, we obtain this final state. Note that this term here is defined as the first term from this multiplication, and all the other three terms, which are actually dependent on the previous pulse, will then come into this state here. And this state is actually a qubit state because this part is independent of JK, and this is a qubit. And this one is a side channel state that is orthogonal to this one here. And importantly, we can now treat our protocol that deals with pulse correlations as a protocol that emits these states here instead of these idealized states. And now we can simplify further this expression by defining the system B as the composite system of all of these, which are all sent to Bob. And note that this includes Alice's and Scylla's because we fictitiously consider an attack on these systems, even though they are not accessible to Eve. We do so to make the maths simpler, but importantly, it doesn't matter how many systems we add as a side channel. What matters is how much our side channel state depends on the setting JK. And this means that this fictitious attack on these systems should not result in lower secret key rates because they do not have any information about JK. So once we make this redefinition, then we finally obtain an equation for the state of the kth pulse. And I would like to remark as an aside that this equation is actually compatible with our previous work, which already treats state preparation flaws, Trojan horse attacks, and spontaneous leakage of information. So this means that we can now put all of these source imperfections together. Okay, so once we have this state, we can then, the next step in the security proof is to estimate the phase error rate. But before I show you how we do it, let me just emphasize that our work also applies to arbitrarily long-range pulse correlations. So more generally, the kth pulse might depend on all the previous setting choices. The good news is that even in this case, even in the case of long-range pulse correlations, we can obtain a state similar to the one we have seen before, so similar to this state. And if you are interested in knowing more about this, I invite you to see me in the meet and greet room, and then I can show you, we can go through all the detailed calculations together for this case. But now let us focus on our objective and continue to prove the security of QKD with nearest neighbor pulse correlations. So when these imperfections are present, this is then the emitted states can then be expressed this way, as we know. And also, we have learned that pulse correlations can be treated as a side channel. So now, to estimate the phase error rate of this protocol and to prove its security, we could simply use any existing security proof that deal with side channels. So we could use the GLLP type security proofs or even the numerical techniques that have been recently proposed. However, these techniques typically require a full characterization of the side channel state, this state here, and some have a poor performance because they are not loss tolerant to state preparation flaws. But fortunately, we have come up with a solution for this too, the reference technique. The reference technique is a framework for security proofs that is very useful to deal with device imperfections, and it can result in high secret key rates. So let me explain you a bit more about the intuition behind this framework. So as with any security proof, our aim is to obtain the phase error rate or the phase error rate as a bound on the mean entropy. To do so, in the reference technique, we first consider some reference states And these reference states should be similar to the actual states. And then using the reference states, we can obtain an expression for the phase error rate. And because we have the freedom to pick them as we wish, we can pick them in such a way that this expression is very easy to obtain. And then, because the actual states are similar to the reference states, their expressions for the phase error rate should also be similar. So the idea of the reference technique is to use the reference states as intermediate parameters to estimate the phase error rate associated with the actual states. So now let's see how we can use this framework to prove the security of QKD with correlated sources. So as I said before, it is very nice if we can pick the reference states such that they are similar to our actual states. And also it is useful to select them such that they are in a structured space, such as a qubit space. If we do so, then we can directly use the loss tolerance protocol to obtain an expression for the phase error rate. And this is important because by using the loss tolerant protocol, we can ensure robustness against state preparation flaws. So now recall that this is our states in the presence of pulse correlations. So these are now our actual states. And note again that here we use the three-state protocol, but this is just an example. So the reference technique can also be used with other protocols. So now using these two advices, we can select our reference states to be these states here. So as you can see, we select the qubit part of our actual states. And these are indeed very similar. So our reference states are similar to our actual states, since this epsilon should be in principle quite small. And an example of these reference states can be these states here. Note that these states also suffer from state preparation flaws. Which we quantify here by this parameter delta. So if delta is 0, then we simply send 0z, 1z, and this state reduces to 0x. However, as delta increases, then we deviate from this ideal scenario. And once we have these reference states, we can then calculate the probability of a phase error. And by directly using the loss tolerant protocol, we find that the probability of a phase error conditional on sending the reference states can be expressed this way, where these are the selection probabilities of Alice and Bob. These are some coefficients that we obtain directly from the loss tolerant protocol, and they can be positive or negative. And these are some conditional probabilities associated with the reference states. So more precisely, this is the probability that Bob obtains the measurement outcome beta, given that Alice selected the setting J. And we call this expression the reference formula, because it will be used as a reference to obtain a similar expression in terms of the actual states. Note that we cannot use this one directly in our security proof because it depends on reference states, which are never used, which are never sent even in reality. But fortunately, by evaluating the deviation between the actual and the reference states, we can bound these probabilities and then obtain an estimation on the phase error rate for the actual protocol. So we call this the deviation evaluation of the reference technique. And this deviation can be quantified using this expression, where here you have some normalized states associated with the actual and the reference states. These are some conditional probabilities associated again with the actual and the reference states, and this corresponds to a lower bound and an upper bound. The mathematical details of this bound are not so important, but it's effectively the bound that was introduced in the low-press skills analysis. We could use another bound to evaluate the deviation between the actual and the reference states, such as the trace distance, but this bound is tighter. Of course, if later on we come up with an even better bound, then we can directly substitute it here and our reference technique would still be valid. So now that we have this bound, we can then transform our reference formula into an expression in terms of the actual states. So recall that our reference formula can be expressed this way. And then using the bound, we obtain this inequality. And here, this parameter is the probability of a phase error given that we send the actual states. So this is the parameter that we want to find in our security proof. These are some states that we obtain from employing the entanglement-based virtual protocol, and these are some joint probabilities. So the probability that Alice selects the setting J and Bob obtains the outcome beta. And since we want an upper bound on this one, here we pick an upper bound for the positive terms and a lower bound for the negative terms. And note as well that these two quantities are obtained from experiments, and all of these gray parameters are actually known from the reference technique or otherwise. So once we have this inequality, we can then directly solve for the probability of a phase error. And once we have this quantity, we can find the phase error rate and then calculate the secret key rate using this expression. And you can see that here we are assuming the symptotic scenario. However, it is straightforward to generalize the reference technique to the finite key regime. And in this equation, this is the joint probability that Alice and Bob select the Z bases, and Bob obtains the detection event. And then, as you know, this is just the phase error rate and the bit error rate. And importantly, to go from this step to this one, all that we needed was an upper bound on the coefficient epsilon. So this is basically all that you need to characterize in your experiment. So no characterization is needed for the side channel states, these states here. And this is very nice because this characterization is supposed to be very hard to do. Of course, if you can somehow do it, then we can add it in our framework, and this would most likely result in higher secret key rates. Also, I would like to remark that existing security proofs that deal with side channels can actually be recovered from the reference technique. So the GLLP type security proofs and the generalized loss tolerant protocol can be regarded as a special case of the reference technique. And then using this framework in the context of pulse correlations, we obtain these results. And here, for the simulations, we have fixed delta. So recall that delta is associated with state preparation flaws. And we have fixed it to this value, but of course we could even choose a larger value of state preparation flaws because the reference technique is robust to this imperfection due to the use of the loss tolerant protocol. So our results would be more or less the same, even if this value increased. And now there are two very important points to note in this figure. First, look at the magnitude of epsilon. As epsilon increases, the deviation between the actual states and the reference states increase. So the deviation from the ideal scenario increases. And this causes a decrease in our secret key rate as expected. And also you can see that to obtain reasonable secret key rates, we need very small values of epsilon. So this suggests that further efforts are needed both on the theoretical side to obtain better estimations of the phase error rate, but also on the experimental side to characterize these parameters epsilon. The second point is that our framework works for long-range post-correlations. So here we have plotted the secret key rate for the case of nearest neighbor post-correlations, so when I equals to 1, but also for second and for 10th nearest neighbor post-correlations. And as expected, the more pulses we consider, then the worse the secret key rate gets. But of course, if epsilon is very small, so if we are close to this ideal scenario, then we can ensure the security of QKD for very long pulse correlations.
Okay. You've had 35 minutes.
Thank you. So to conclude, we have introduced a simple formalism to deal with pulse correlations. So basically, we can treat the information encoded in the subsequent pulses as a side channel to our pulse of interest. We have demonstrated that the state emitted from a correlated source can be expressed this way. And it turns out that this is in fact compatible with our previous work, where we show that a more general version of this equation already takes care of state preparation flaws, Trojan horse attacks, and spontaneous leakage of information. So this means that we can now put together all source imperfections into the security proof. Moreover, we have proposed a new framework for security proofs, the reference technique, which is very useful to deal with any kind of device imperfections. And finally, as we have seen, MVI QKD type of protocols can remove all the side channel attacks on the detector side. So then if we combine these protocols with what I told you about today, we can actually guarantee the implementation security of QKD. If you are interested about this, I invite you to check out our latest work on arXiv, where we propose a very simple and practical protocol that is secure against any side channel. So basically, this is the only protocol together with device-independent QKD that can claim implementation security of QKD. Okay, so thank you very much for your attention, and I'm happy to answer any questions. Thank you.
Okay, thank you very much, Margarita, for this nice talk. So now we can move to the Q&A. Yeah, please type your questions into the Q&A. We currently have 2 waiting, so we can start with Fred asks, roughly how big is epsilon in typical QKD experiment?
Well, that's a very good question, but currently we don't know. So epsilon has not been characterized. So this epsilon, I should say that it can be any kind of imperfection. It can include not only post correlations, but also other imperfections. And this epsilon and characterizing how big it is the next big challenge for us. So unfortunately, I don't have an answer to the question.
So you don't have a technique even to estimate or bound epsilon somehow, or like given a model of a device or something? At
the moment, we really need the help of experimentalists, to be honest.
Fair enough.
So of course, you can always put a bound on epsilon. So you can always say, okay, I don't know what are my side channels, but epsilon cannot be bigger than this, right? So you can always do that. But ideally, in a security proof, you will go. You will do some kind of characterization to learn exactly like how much this epsilon would be. So yeah, we need all the help we can get and all the interest so that we find this epsilon.
Fair enough.
Great, and there's another question from Ignatius William Primadja. I think your microphone has been unmuted, so would you like to ask it directly?
Yes, thanks for the talk. So I have two questions. I think the second one is pretty much answered. So the first one would be like I suppose in this three-state protocol, you would require some form of like decoy state method. And how would the past correlation affect the decoy state implementation, and how would it affect the overall security analysis?
Okay, thank you for your question. So here in this case and in our paper, we treat, we don't take into account the decoy state method because we are just talking about correlations in the phase modulator. So here we actually, in our model, we assume a single photon source. However, if you consider a coherent source, then we would need to use the decoy state method. But in this case, as you said, we would need to take into account as well the correlations in the intensity modulator. But in principle, this should not be a problem. And in fact, our group is already working on how to extend this to that scenario.
All right, thank you.
Thank you.
Okay, and we have another question from Tim Spiller. I think you've been unmuted. You want to ask directly?
Okay, thank you. Hope you can hear me. I'm just interested to know, given the similarities between a QKD source and one that's used for generating quantum random numbers, whether your techniques can be applied to look at pulse correlations between the successive pulses in a quantum random number generator.
Thank you for your question. I would say maybe, but I don't know for sure. I would need some more time to look into that problem and to then tell you a more concrete answer. At the moment, I cannot say for sure, but I think that our description of the state is very general. So in principle, it could apply to those correlations too. This is just my guess.
Okay, thank you.
Thank you.
Okay, let me just ask one quick question. So you're sort of pushing towards getting independence from the sources and from the detectors. How close is this to being completely device independent, or how would you compare this to something that is completely device independent?
Thank you. So I would say that this is completely device independent. Actually, when you combine it with an MVI type protocol, I would say that this would be completely, yes, device independent, because the MVI type of protocol will take care about will take care of the detector side, and then if we are able to characterize all the possible imperfections on the source, then we can actually ensure implementation security. So the only thing we would need to characterize from the experiment is just this parameter epsilon, and once we do, yes, we can pretty much guarantee practical security the same way device independent does.
Okay, but you need to characterize this epsilon, right? So all of the I mean, there is still some device dependence left, or something in the sense of characterizing this, I guess.
Sure, but I believe that in device independent QKD, you also need to characterize some things. No, I don't know much, so but. What I know is that in device independent QKD, you also don't assume that, as far as I know, that you have kind of leakages, right? From.
I mean, you have to assume that there's a secure laboratory.
Exactly.
Leak,
so the same way in device independent, you have to do some kind of obtain some parameters from experiments. Here you do too. but in the end, they both can achieve the task of guaranteeing implementation security.
Okay, yeah, I mean, I would say that the assumption about the strong walls of the lab is not really an experimental thing that you obtain. It's more like the same. I mean, I guess you're also making that assumption that you assume that your lab is not leaking.
We do assume. We do assume that we can have leakage of information, no? Because we take into account Trojan horse attacks, for example. So we do assume these kind of leakages.
Okay, but not an arbitrary leakage. Like you cannot have a tiny robot in your lab, for instance.
I mean, we assume passive leakages too from the devices, but having a robot, that one I never thought about. So I'm not sure.
But I mean, is this kind of no leakage assumption that you make in device independence?
No, again, we do not make an assumption that we don't have no leakages. I would like to emphasize that here we take into account those leakages.
Yes, no, I was saying in normal device independence, it's kind of no robot assumption is the analog of the assumption that you're making. It's not really a experimental parameterization. Anyway, let's. Okay, actually, Marcos Curti wants to add something to the discussion on this.
Yeah. Hello, can you hear me?
Yeah.
Yeah, no, it was basically, I think it has been already discussed. So this is an alternative approach to device-independent QKD. So on the one hand, we have device independence as a way to try to achieve implementation security where we don't need to characterize the devices. That is clear. But there is also doubt about its practicality and what kind of rates we can get at certain distances, okay? So of course, there's much work on that and things might improve, but right now, indeed, there is no experiment on device-independent QKD. And also there are some assumptions on device-independent QKD that have been already mentioned, at least in the current version of security proofs that wouldn't hold in practice. Typically, this is the problem of information leakage that you have already raised. So an alternative solution would be to try to characterize the devices. So, and this kind of solution has been always believed to be very challenging, and maybe indeed it is also challenging. So in this is the path that we have followed in this work, but we have tried to simplify it as much as possible, although there is still the question whether it's easy or not experimentally to really measure or get a lower bound on this epsilon. But we managed to basically put all possible imperfections, including information leakage. So we include all possible device imperfections on the transmitter just through one single parameter epsilon, including pulse correlations, information leakage, state preparation flows, whatever wrong things can go in the transmitter. And then, as Margarita already mentioned, we just save the detector through measurement device independent QKD. So which approach is better? Well, we don't know. So we will see which one is more practical. Right now, both are challenging because this approach also needs to really be able that experiments match this small epsilon. But we are optimistic that probably this could be done eventually. That was what I wanted to say.
Okay, thank you. Yes, I mean, I think it's very nice if you can sort of collapse everything you need to know about the device into a single measurable, in principle, measurable parameter. So yeah, thank you for that comment. Are there any last questions? I don't see any.
Well,
so,
I sort of had a
slightly
follow-up
over
question.
the time anyway, so I think we'll end the session there. So, sorry.
You can ask me later.
Yeah, maybe I'll ask later.
It's a question in the chat. Okay, go ahead, Fred. It seems to be a quick question.
Yeah, it was just a follow-up question to so I was just wondering how the actual rates compare to the best rates we can get through the IQKD, right? So it seems to be pretty expensive in terms of epsilon, but it's kind of hard to compare to the kind of rates you would get from the actual device-independent experiments.
So we haven't yet compared directly these two approaches, but we are actually at this moment working on it. So very soon you will be able to see exactly how it compares. But our prediction is that it will be better than device-independent QKD.
Sorry if I can also add something, because
Yes.
actually we know already some of the rates, for instance, for device-independent QKD, depending what kind of technology you assume. For instance, if you assume parameter down conversion sources, of course, if you assume perfect Bell states, the performance will be better. But if we are thinking about something practical with current technology and we just take parameter down conversion sources, then we know that in device-independent QKD, we cannot tolerate much losses.
Right.
So unless one uses a kind of device, qubit amplifier, for instance. And if one assumes even a qubit amplifier, typically the kind of attenuation that one can tolerate is about 10 dBs or 12 dBs, depending on the channel model. And the rates are very, very low. So actually just looking to the figure that is in that Margarita has in this slide, we know that the rates of this approach are significantly much higher, several order of magnitude, and also can reach much longer distances. Okay.
Okay, thanks.
Okay, very good. So we can now